So in this section, we're going to talk the thin airfoil theory. We're going to derive all the equation, and the next one we're going to apply them for 2 dimensions. Before we move on, let me just review what the Karakowski Theorem means. First of all, it is very fundamental in the study of aerodynamics. It's very important, and it relates the lift by the airfoil to the speed of the airfoil. If we remember, if this is equal to 0 from a previous discussion, we show that this was equal to V infinite times the circulation, right? So that's where this equation actually comes from. The circulation is defined around lines integral. So I mean, when I go from here to here, this is just stagnation point. So 1 and 2 are there. So what you're really saying is that the closed loop around this of this ds actually is equal to 0. So you can say circulation 1 is equal to circulation at 2. Okay. So as we move on, let's understand how these theories actually work in this context. So first of all, we're going to, this is going to be your angle of attack. So this is coming at an angle alpha. It's actually given here. This is the location where your speed is actually intersecting the camber, or a straight line between the trailing edge and leading edge, and the trailing edge, if you draw a straight line, and that's the angle in which that your wind is actually, your stream velocity is hitting here. You have the lower camber, you have the upper camber function. This is how the functions are given. And basically what we're going to do in our analysis is we're going to consider the following. I'm going to have a velocity component in this direction. I'm going to have a velocity component in this direction. So let's call this velocity component. This is your V infinite. This is your small velocity component B. And then we're going to give it a small perturbation. So we're going to say there's going to be a small perturbation in U. We're going to call that perturbation U prime. And then you do have this velocity there, V. And we're going to add a small perturbation to this, call it V prime. Okay, so the total resultant now is basically your vector V plus a vector Q. So what we are trying to study is what happens in the small perturbation state, and that's what's going to give us all the equations that we are really interested in. Okay, so when we are doing this analysis, remember, we are assuming that there's a potential flow that does exist, and this is end result. If you remember, the gradient dot V is equal to 0. So this is potential flow. You can replace, you can show that this is given. And again, this comes from this perturbation analysis assumption that I just told you in the previous segment slide. And then here, so basically what you're saying is, let's assume that this over here is your upper function, and this is nothing like eta x, and this could be your lower function, low eta L of x. What is important to know is a couple of things. First of all, if your airfoil is symmetric, then U is almost equal to eta L, right? Well, actually, it's equal to, because it's symmetric. The distances are the same. Second thing that you have to know for thin airfoils, what you have is this is approximately equal to this, and it's basically equal to 0. Because these are same, this is going to be identically to 0, and this is the only thing that will be not 0. This is, again, remember, for thin airfoils. So then basically this is equal to this, and this is nothing else than the chord. Okay, the total length will be the length of the chord. That's what this is basically telling you. So before we, okay, as we continue, let's suppose we take a boundary right there at any point and we want to understand what happens at the boundaries. We're going to call those boundary conditions, and we talked about that before, but I want to expand on that for a while here in the next couple of minutes. So we have the velocity vector, which we know that's given by the potential, velocity potential. And recall that this velocity in general using is going to be a vector of u infinite plus your u, and this is going to be a prime, and this is going to be v prime. Okay, so this is important for you to know. And then this is given by the gradient of f over the magnitude of the gradient of f for a two-dimensional structure, for a two-dimensional case. That's probably better understood by doing this. So if I have a velocity coming in this direction and it's coming at a unit normal to this, so this is normal. So what you're going to have is the normal is equal to the gradient of f, where the gradient of f in a two-dimensional case is partial of f respect to x, partial of y respect to y. And then this, just know that in general this is a function of x and y. It's x and y because eta is a function of x, and this is just a function y. That's what is a function x and y. Okay, so if I take this now and I replace it in here, right, and I replace this in there, which will give me this, we'll actually end up with the following condition. Okay, so let's move on. So in this equation, what I have done is I have taken the same, there's primes missing here, and again, being a little bit sloppy, sometimes I keep the prime, sometimes I don't, but you should know that this is actually the perturbed speed. That's what we are trying to do. So I take this speed and I take the dot product with this to make sure this is equal to 0. That's where these two equations come from. Okay, this equation comes from. Now we know for a fact these two are very, 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 very small. Since they're very small, then this basically equation becomes this equation right here. And so I can take this equation and I can solve for b. That's what I have done here. Solving for b gives you this equation. And also know that on the body of the surface, okay, I can show that this is also has to be value, has to be 0. So by replacing these equations inside there, you can see this is a constant. I choose the constant to be equal to 0. Okay. So the potential velocity potential for this flow, this is the stream, and this is the flow because of your airfoil, what's happening around your airfoil. And these are just your standard equations that we are used to, you know, in Cartesian coordinates. Here we are now working in polar coordinates, so that's basically straightforward equations that you know. And please feel free to pause this video anytime to take your notes. So if I continue, first, there are a couple of assumptions we're going to make, okay? So I'm going to assume there's no viscous effect. That means this is equal to 0, so that means that this equation, partial of u respect to y, this is actually equal to 0. There's no shear involved in my problem. We are assuming that your angle of attack is really small. Since this is small, these approximations are valid. This is only good for small angle of attacks. And so we are, another consequence of this, if I take the derivative of these equations, they are basically of the same order. That's because angles are very small to each other. Okay, otherwise we could not do that. And and that's also a result, as the consequence of this, the result of this is that the disturbances are very small. That's why we can say the angles are small too. Okay, so some consequences of my assumptions. I can use Bernoulli's equation because remember I have a potential flow, so that means an ideal flow. And remember this equation, we have used this several times now. So what I'm going to do is I am going to start and try to find what CP looks like for my my equation. And if you real, I'm going to take this big equation that I have here. V is equal to this expression right there, just that expression. And I'm going to replace the whole thing in here. That's the velocity. Again, just this is u infinite cosine of alpha I plus u prime at I plus v prime u infinite sine of alpha plus v prime at j. That's your velocity. Take dot product of the same velocity, gives you this big expression. I will plug this expression inside there and do a little mathematics. You can show that actually simplifies to this. We're going to keep working with these expressions until we find something a very nice closed form solution. So we keep working a little bit of mathematics, not so much interested that you understand the whole derivation, then you understand this at a higher level. So remember, because I told you that this is far smaller than this, right, squared. So if I take and I square this, it becomes even smaller. So basically all these terms, basically these are second order terms that basically vanish. They are actually equal to, I can ignore them. Then at the end of the day, you end up with this nice, beautiful expression, which this is what we will be using. Okay? And note that your u prime is nothing else than, again, we use u prime just for u, but then this is nothing else than your potential velocity. I don't have v's, otherwise this would be in function of y. And the goal then is, in order to find your CP, I want to find an expression for phi. Okay? So the goal is, what is the potential flow for my problem? Or can I find an expression for this so I can find my coefficient of pressure? Now the coefficient of pressure is very, very important, because that's what's going to give me my lift. Just as a review, remember, if I have pressure at my upper surface and pressure at my lower, so delta P is related to your delta CP, right? CP at the top and at the bottom. So, and that delta P is what's going to generate your lift. Okay? So your delta P is actually related to delta CP, which is going to give you a delta L, which is going to give me what is going to be the expression for your total lift. Similarly for drag later. So in order to get those expressions in, let's go ahead and move on and let's work with your boundary conditions. Remember, in our problem, first of all, these are very, very small compared to these. And furthermore, what we can say, this velocity term right there is given by, so I can solve this, so I can take this velocity term and equate the velocity term to this. That's the end expression by basically assuming this is very, very small. Assume that some of this does exist, then this becomes this. So I can solve for this. Okay, so this leads me to the next chart right here in our derivation. So what you do here is, since eta is very, very small, and at the boundary, the chord line, that's what we are saying, right? That this is basically, we are working at the chord line because we're working a thin airfoil. Then basically we can use Taylor series expansion. We tend to do this very often, where this is equal to this expression right here, okay? And then this term, basically, this term, we don't need this term right here, so we can say this is, because it's very small, this basically becomes equal to this term right here. So because this is a thin airfoil, remember, in thin airfoils, eta is basically equal to 0 because there is no eta. You see, you have this distance y, but it's thin, so y is basically buckles up to 0. Okay, so this is a nice expression, and this is going to be very helpful in deriving these equations. So now I can say I have a velocity at the top surface, velocity at the bottom surface, although I assume they were 0. Let's separate both of them, and then I can further work with these equations in our next slide, and just know that nu is almost equal to this. So this is basically this is another way to write my upper and my lower, but your thickness is basically equal to 0, so the whole thing is basically going to be equal to NC at the end of the day. But let's go and derive the equations, and then later we will do that assumption. Okay, so that's what these equations, then I plug these equations back in here, and that's where these equations come from, replacing these in there. Remember the cutout conditions that states that your velocity at the upper and at the bottom have to be the same. Okay, so that's what this is saying. This is upper, so you can call this V1, you can call this V2. They have to be identical. That's what your cutout condition is saying. And so now what we're going to do is, and remember what we are trying to do in the problem is we are trying to find the expression for CP. Don't lose sight of what we are really trying to do here. So in order to do that, let's satisfy the boundary conditions. And to satisfy all my boundary conditions, what we're going to do is we're going to do the following. We're going to divide the problem into, say the whole problem here is going to equal to the thickness, the camber, plus the angle of attack. 3 parts of the problem. This problem, by the thickness alone, tells me that this expression plus minus equal to V infinite partial of eta t partial of x. Because we have a camber, or we can have a camber, then plus minus equal to the camber. And because we have an angle of attack, that's your stream velocity, that's going to equal to this. Okay, so we got 3 different expressions, one for the thickness, one for the camber, one for the angle of attack. And then what we're going to assume is that your entire model is like a vortex. So we are studying and analyzing the whole thing using a vortex sheet and a source sheet. So we just used equations that we learned previously with the body, aerodynamics around the general body. Those apply. So this is basically the vortex strength. This is the source strength. Let's call it Q by unit length. Then what really happens in our problem, if I use that, just know before I do that, the airfoil is going to generate some discontinuity in the upper and the bottom. The magnitude of the discontinuity is going to be controlled by the shape and the angle of attack alpha. Generates a velocity v. This velocity right there is the responsible for that discontinuity. However, regardless of this discontinuity, we assume that the Karakowski Theorem applies in here in the end. So that's very, very, very important. Okay, so let's start with this discussion right here. So what happens with the source and what happens with this point. So let's suppose we are working at the location x1. So in this model, we're going to assume I got a point right there, and I'm moving to a point P, and I want to know what happens at that point P. This is what I'm going to call my angle theta. And this is nothing else than the distance. This is the distance from vortex at x equal to x1 to point P. Okay, and C, it represents C represents the chord of airfoil. Okay, so let's go back to what we learned in the previous segments and let's pull it all together. And if I can write this for my u, this is qx1 d of x. And remember, this is just coming from the strength. This is coming from the strength of the from here. This is coming from the source sheet, and this is coming from the vortex sheet. So then dv is equal to gamma x1 d of x1, 2 pi x minus x1. Now at y equal to 0, remember we are working with thin airfoil. So your distance, this total distance is actually equal to 0. So if I did that, then you can show that this velocity is 0 to c is equal to q of x1. Don't get scared with the nasty integrals here. They greatly simplify, and I will show you how to do that in a few minutes. Let's just finish the derivation. That's what we really need to do right now. Divided by 2, and then your v is equal to 0 to L. And you can show that this is what your end result is. Okay? So if we move on, now the same thing at y, although is equal to 0, remember, but 0 plus, assume there is some thickness there involved. Then here the equation will be 0 to c. The only difference here is the plus sign, is the plus minus get inverted. 2 pi x minus x1 d of x1. This now becomes plus. And the second equation becomes 0 to c, gamma x1, 2 pi x minus x1 d of x1 minus q of x is equal to divided by 2. And please remember, don't forget the cutoff condition. The cutoff condition for this sheet says that this is actually equal to 0, and this is basically happening at the chord. Okay, remember we are basically assuming I have taken the whole thing and I have converted the whole thing into a sheet, a very, very, very thin sheet. Okay, so now I'm going to go ahead and I'm going to proceed. Pause the video, you can take a screenshot or write it, whatever works for you, that's fine. So now I'm going to expand the whole thing, the right hand side and the left hand side, what your velocities are. Remember, we derived this right here. Your velocity is equal to this. From that slide right here, then I can show that this whole thing becomes this. And this has to be true such that these conditions are met in this problem. So if I keep on moving this, and what I'm going to do next is, don't lose sight, we are trying to find CP in our problem. So let's just remember that. And so we're going to come back to this equation in a minute. So we're going to go, we need to find these values such that we can find this pressure. Okay, and we know that the upper and the lower segments of this pressure are given by these equations right here, and we just derived this a few minutes ago. So what we want to do now is we want to go ahead and start with these equations. Okay, so in order to find what an expression for these, we're going to continue with this set of equations. We're going to come here, and what we're going to do is we're going to add these equations together, and let's see what happens. Okay, So we add all of this. This gives you minus 2 alpha plus 2 times partial of eta c respect to x. This cancels out. This cancels out. This gives you plus 2 times 2 pi v infinite 0 to c gamma x1 minus x1 respect to x1. Okay, so we can keep working with these equations now, and we have the following. So to solve for this equation, make a small substitution. Again, I'm just telling you how this is done. I'm not expecting anyone to be responsible to know this whole derivation. Cosine of theta 1. So then the whole thing becomes minus alpha plus, and then this was x instead of x. I'm going to replace this for theta. So this, the whole thing now, this expression has to be a function of theta. And 2 pi v infinite, 0 to pi. Why 0 to pi? Because we are going to the chord, going 0 to c. This is the same as going from here to there. Okay, so we are doing 0 to pi. That's what we're doing the integration. Theta 1 and cosine of theta 1 minus cosine of theta d theta 1, and there is a sine of theta 1 there. I know the integrals kind of look nasty as you see them, but they are really not that bad at all. At the end of the day, you will see there's some closed form solutions to this. So at the end of the day, my whole expression is equal to this. 2v infinite a sub 0, 1 plus cosine of theta, sine of theta, minus 2 times v infinite, summation of n equal to 1 to infinite, an sine of n theta, okay, where it's been shown that this is equal to 1 over pi, 0 to pi, partial of eta, partial of x of theta, d theta minus alpha, an is equal to 2 times pi, 0 to pi, partial of eta, x, theta, cosine of n theta, d of theta. Okay, so now we have an expression for these for CP. I can plug everything in there in the equations that we have, and know then this expression. But we really, if we had this and this, which we just found here, an expression for this. So I'm going to replace the whole thing in there, and you can stop and take a screenshot of this or write it. You end up with the following expression. CP theta 0 plus minus is equal to plus minus gamma of theta v infinite plus 2 times summation of I equal to 1 to infinite bn cosine of n theta, where bn is equal to 2 divided by 0 to pi, partial of eta t, partial of x with respect to theta, sine of n theta d theta. Okay, so how to deal with these expressions, we will learn that later as we do some examples. But this basically gives you the coefficient of pressure that we really need at the upper and the lower part. So once we have the coefficient of pressure, that's what we were looking for from the beginning. That's where we went through this journey. So we have this nice expression now. We know what it looks like. So now we can go ahead and determine what is the lift. To find the lift, we're going to do the integration. We're going to integrate this pressure. Or in other words, simply apply Karakowski, the Karakowski Theorem to your vortex strength, and that will give you, first let's calculate the lift. We know the lift is calculated over, in general, is calculated 0 to my span, to my chord length, upper times B times d of x. Note that PL is equal to 1/2 rho v squared CP x comma minus at the upper surface. So this is nothing else than CP lower. Then PU is equal to 1/2 rho, and this is all that is stream V infinite squared. CP at the up is 0 plus, and this is CPU. Okay, so that is given by this. Second is calculate the moment. Positive about x1, and that's going to give you the following expression. M is equal to 0 to C, PL minus PU, x1 minus x times B dx. Or basically I can divide this whole thing 1 rho V squared B times C squared, and that gives you coefficient of moment is 1 over C, 0 to C, CPL minus CPU, x1 over C minus x over C d of x. And note that these expressions right here are given by this. CP, this is CP up, and this is CPL. Okay, so once we have all this expression, which we do, okay, plus minus is going to give you by this expression right here, then we can plug it inside there and integrate. Similarly, I could do the same thing here, 1/2 rho V squared infinite times BC, and this is your coefficient of lift, and that will give you 1 over C, 0 to C, CPL minus CPU d of x. This is C. Okay, and then the last thing we need to know, one of the last things that we need to derive in these equations is the aerodynamic, two more things, the aerodynamic center. So the aerodynamic center will be the location where the derivative of your moment is actually respect to your lift is going to be 0. And we like to call this the derivative of the moment about the aerodynamic center. So we call it AC, sometimes smaller AC. Partial in respect to dl has to be 0. Or we can expand this because we typically can take the derivative of this respect to your angle of attack, CL, and this has to be 0. Or this can only be 0 if my upper part is actually equal to 0. So to find your aerodynamic center, this has to be CMAC vector alpha is equal to 0. Either expression gives you the same answer depending on what you have. Okay? Number 4 is the center of pressure. Center of pressure of the airfoil, and the center of pressure is very easy to calculate. Is given by the center pressure will be the aerodynamic center minus moment, the aerodynamic, divided by coefficient of lift. If we do that, that will give you the values that you're looking for. Okay, so we can also express everything in terms of your coefficient of the coefficient of lift can be also be expressed in terms of your circulation as we have done in the past. So the coefficient of lift and circulation will be L is equal to, we already derived this, 1/2 rho V squared times B, 0 to C, CPL minus CPU d of x. And this will come from the following equation. If I subtract upper minus lower, you can see this cancels out. I'm just left with this expression here. So if we did the whole thing, you can see that this whole thing is basically nothing else than the following expression. V infinite squared, P, 0 to C, gamma x of V, d of x. Note that when you subtract, these two cancel out, you just end up with these terms. And then just recall that your circulation is nothing else over a sheet. Remember, this is a sheet, a vortex sheet, is nothing else than the integral over the entire vortex. So from here, your L is equal to 1/2 rho V infinite B L over V infinite. Or we can also write it as 1/2 rho V squared times C, B, and your coefficient of lift. Okay, so this is how we relate this. So this is all the derivation for thin airfoil theory, all the equations that we need.